Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to give you the general definition of a toric variety, which is a wonderful variety that you can define using the combinatorial data of a fan, and hence you can also study combinatorially. Okay, so let's see our general setup. We're going to start here with a pair of dual abelian groups. So n will be just z to the n. And we'll also need to know what happens when you tensor that n with q to get q to the n. M will be its dual, so that's just going to be the homomorphisms of that abelian group n into z. So that's just another copy of z to the n, and you can identify it with z to the n if you use the usual Euclidean inner product. And it's toric geometry because this choice of abelian group essentially corresponds to the weights of a torus. And what's that torus? The best way to write that is just the group homomorphisms from M to K cross, where K is the algebraically closed field that you're dealing with. Okay, so the combinatorial gadget that we want to introduce now is called the fan. So let's see what the definition of a fan is. Okay, and previously in this playlist, you would have seen examples of fans before. So it'll look a little bit like something like this that you see here. This is the fan associated to P2. So what is a fan? So firstly, it's just a collection of strongly convex cones inside this n tensor Q. So this is just some vector space, n-dimensional vector space over Q, right? So it's a collection of strongly convex cones. And remember, strongly convex means that in this cone, the only vectors inside there which are such that their negatives are also inside there is the zero vector. Okay, so that's what strongly convex means. And this collection of cones, you don't want it to be arbitrary. They have to satisfy two axioms. So the first one is that we want it to be closed under faces. Every face of any sigma inside this collection delta of strongly convex cones is in delta. The other thing that you want is that if you have two cones inside delta, okay, you take the intersection of them, okay, so that's some subset of this Q to the n, and you want it to be a face of both sigma and delta. Okay, so let's just look at a simple example. So this diagram here is supposed to represent such a fan. What you'll see in this fan is firstly, you'll have two-dimensional cones given by sigma and tau. Okay, so remember each face of a cone inside that fan has to be a cone in that fan. So what are the faces? So firstly, the one-dimensional faces of sigma are this face here and this face here. So they're also cones inside this fan, as well as the faces of this tau. So that's this one here and this one here. They're the one-dimensional faces. And the zero-dimensional faces, well, that's just this point here. Okay, so note all of these cones, they're strongly convex. If you take any vector in sigma, for example, okay, and look at its negative, it will not be inside sigma unless, of course, it's zero. So they're strongly convex like that. Okay, so we've seen how many cones in this fan: 1, 2 two-dimensional ones, plus 3 one-dimensional ones, and 1 zero-dimensional one. So 6 all up. Okay, so it's that collection of 6 strongly convex cones that's going to form our fan. It's easy to see now that actually if you take the face of any of them, okay, we check the faces of sigma and tau, but if you check the faces of any of them, there'll be a face inside that one. So for example, if you take the faces of this cone here, this one-dimensional one here, the only proper faces is the zero here, the zero-dimensional one, and that's also a face, a cone rather, in this fan. Okay, so what about the second axiom? Let's check the second axiom now. What you need to do is you need to intersect any two faces inside here and check that it is a face of both of them. Okay, so intersect any two cones inside here. Okay, so the ones that's easiest to see is sigma intersect tau. When you check the intersection, it's just this diagonal ray here, and that intersection, of course, is a face of both sigma and tau. So the important thing is that here you can see sort of two triangular shaped or angle shaped cones, and when they intersect, okay, they can't overlap in some sort of two-dimensional region. Okay, so that's one of the things that you want to happen, and that's the way to kind of think about this second axiom. Let's do another example. Let's intersect this sigma, this cone here, with this cone, which is the positive x-axis, if you like. And then the intersection is just the 0 here, and that's a face of both this one and of this cone sigma. Okay, and you can check through all the other pairs of cones to see that the intersections of cones is indeed a face of each. Okay, and it's fairly easy to see that from the picture as well. Okay, so that's the data that we're going to use to construct a variety, and it's called a fan. So what is the associated toric variety to this fan? Okay, often it's going to be denoted by this x delta, and the way we'll do it is using the manifold style of construction. Okay, so we're going to give you some affine open cover, and then we're going to glue those affine open covers or those affine open subsets together. So what are the open sets in that open cover? So firstly, for each cone sigma inside your fan delta, I'm going to give you an affine open subset. Okay, so what I do is I take that sigma, and now remember the sigma is inside here. We're going to look inside the dual, and we'll get the sigma check. That's inside this rational vector space. Then we intersect it with these lattice points. So that's the M inside the dual space. So that's M sigma check. That's essentially just the intersection. Okay. And since this is a monoid, we take the monoid algebra of that, and then we look at the spectrum of that. So in other words, the points of this is just the monoid maps, okay, the multiplicative maps of this monoid into K. That's going to give you the points, okay? And we're going to denote that with U sigma. Okay, so now we have a collection of affine varieties. And the next thing that we need to do is we need to know how we glue these together. And how do we glue them together? So suppose we have a sigma and a tau. They're two cones inside our fan. We're going to look at the intersection of these two cones. Okay, we'll call that rho. What we're going to do is firstly realize that this rho, because it's the intersection of these two cones, okay, it's going to correspond to a principal open subset. Since there's a face of each of sigma and tau, it's going to correspond to a principal open subset of the U sigma and the U tau. Okay, so if we look now at rho and we look at rho check, and there's M rho check, that's one of the affine varieties that we have inside this cover. But actually, it's gotten from Km sigma check and Km tau check by localizations. In fact, more precisely by inverting by a single element. So this will correspond to, so remember we have these inclusions, so we have maps the other way on the spectra, okay, on the affine open sets. And in fact, they're just inclusions of principal open subsets. And since we have an inclusion of a principal open subset into this, will give us U sigma, and in this side, it will give us U tau. We've identified open subsets of U sigma and U tau, and that identification gives us the gluing of, one open subset of U sigma to one open subset of U tau. And we do that for all pairs sigma and tau, and then we get our variety. Okay, so before we go on to give a very simple example, let's just make one remark. In what sense is it a toric variety? Okay, so the first thing is that, well, each of these, remember, is a toric variety. Why? So the key point about how the torus sort of reduces things into combinatorics is in representation theory. When you study that, you can use the theory of weight spaces. And the weights are indexed by basically this abelian group Z to the n. Okay, and in particular, when you look at this monoid algebra, this monoid here, M sigma check, is going to be contained inside M. Okay, so this has a weight space decomposition, so the torus acts on this and hence on the spectrum. Okay, and then the other thing is that, well, now So all these coordinate rings of these affine varieties which make up this associated toric variety, okay, if you look at them, now let's look at these inclusions. These are all graded algebras, right? They're all z to the n graded algebras or m graded algebras. And these morphisms are also graded. So that means that the torus action respects the gluing. So that means that you can not only let the torus act on each of these individually, but you can act on them all simultaneously, and it respects the gluing, so you have an action of the torus on the entire toric variety. Okay, fantastic. Let's have a look at our first example of a toric variety from the general setup. And this is the simplest one that you can sort of get, which is interesting, okay, so which is not affine. And what we'll do is we'll just look at the smallest possible case where n is equal to 1. Okay, so we're just basically inside q to the 1, just the rational number line. Okay, and what we'll do is the first cone that we'll have here is we'll just take a basis vector 1, okay, and we just look at the non-negative rationals times 1. So basically here we've just got the sigma is going to be all the non-negative rationals. So it'll include 0 and go all the way up like that. So that's one cone, and it's certainly strongly convex. Okay, we didn't contain the negatives of any of these elements other than 0. And then we're going to have another strongly convex cone to form this fan delta. Okay, and that's going to be the non-positive rationals. Okay, so if you want to check, it's quite easy to check that will give you a fan once you also throw in the face. So what is the face? There's only one face, and that's non-trivial, and that's the 0. That's the intersection of tau and sigma. Okay, we'll call that rho. And once we throw that in, of course, we'll see that 2 is also satisfied. Okay, so the intersection is also face of each of them. Okay, it's a face of tau and of sigma. And that's the first example of a fan, which is non-trivial, doesn't contain just a single cone or a single cone and its faces. Okay, so it's more interesting. It has cones, and not all of them are faces of a single cone. Okay, so what's the next step? Okay, so remember, this is the data that we use to define it, but to actually construct the toric varieties, we look at the dual situation. Okay, so the dual cone and the dual abelian group. So we move from n to m now. I'm going to go from n to m, and we can use the Euclidean inner product, the usual dot product, to identify this m with z. Okay, and also the dual of q would just be q. So what's sigma check? Sigma check is just all those things such that when you multiply with anything inside sigma, okay, it becomes non-negative. So that's also just the non-negative rationals. And similarly, tau check is just the non-positive rationals. Okay. So now what we can do is we can look at all the possible open affine varieties, okay, which cover the corresponding toric variety. And there are only 3 faces to deal with, okay, sigma, tau, and rho, so we can look at all of them, okay. So let's look first at sigma. So the corresponding U sigma, look at sigma check, okay, so that's the non-negative rationals. Sigma check, I intersect that with m, so that's the natural numbers. And if I look at k of the natural numbers, okay, so what's that equal to this monoid algebra? Well, you can identify n, okay, with all the non-negative integer powers of x. So this is just kx. This monoid algebra is just a polynomial ring in a single variable, which I've called x. Okay, what about tau check? It's exactly the same. You look at tau check, okay, it's the non-negative, non-positive rather, rationals. And then you intersect that with m, so you'll get the non-positive integers, so k minus n, so that's naturally kx inverse. And the final cone that you have in this fan is just the intersection rho, that's just 0. So rho check is 0 check, and what's has non-negative intersection with 0, or any rational number you like. So that means that this km rho check, okay, you intersect this with this m, which is z, that's kz. So you just have here this kxx inverse here. So what do you have in this toric variety? So you have three affine open sets. Okay, this here corresponds to just the affine line with variable x, just the affine line with variable x. This here is just the affine line with variable x inverse. And you're going to glue them together. And how do you glue them together? Here, this tells you how to glue it. This is the localization of this by inverting x. So you removed x equals 0. And this is also the localization of this one here. You've just thrown in an x, which means you invert x inverse. Okay, so you remove the x inverse equals 0 or the infinity. So basically, what you've done is you've added a point to infinity here to get the projective line. So this is one of the standard ways to construct the projective line by gluing two copies of the affine line to each other, okay, along this principal open subset. And there you have it, okay? The construction of P1 as a toric variety, and it uses this combinatorial data to do so. Let's look at a more interesting example where we move now to the case where n here equals 2, so it's two-dimensional. So we've looked at this fan previously, okay? So it has two-dimensional ones, sigma and tau, and then we throw in all their faces as well, okay? And that's what we get. So that's step one, okay? But to actually get the affine varieties, we have to move to the dual cone, so we're going to move over to M. Okay, so let's just go through this slowly. So the first thing you want to do is you want to compute sigma check. So you want to have non-negative intersection with everything inside here. So the key points is to have non-negative intersection with this ray up here. So in other words, the second basis vector, okay? So you want to be above this x-axis, okay? So we've drawn this in the orange here, okay? And you want to have also positive inner, or rather non-negative inner product with this ray here, so with 1, 1, for example. So that means that you want to be above this bit here. So it's this orange shaded region that you see here, okay? That's sigma check. And you can do the similar thing with tau check, okay? You just swap the roles. So I guess you can just swap these axes and you'll find it's the purple horizontal lines that you see there, okay? So it's to the right of this y-axis and it's above this diagonal line, okay? So that's the tau check. Okay, so okay, let's keep going. So we've got lots of affine open sets because we have lots of cones which form this fan. But I hope you can kind of see from this example that the most important ones come from the highest dimensional cones. Okay, so we're going to look at sigma check and tau check. All the other cones are faces of these. So they correspond to principal open subsets, okay? So really these ones correspond to sigma and tau. They're the ones we want to look at. So we look at Km sigma check and Km tau check. Okay, that's what this recipe requires us to do. And their spectra, okay? So they'll be the coordinate rings of the associated affine open sets that we want to use to construct our toric variety. So in other words, so we'll see straight away that our toric variety here, x delta, will be covered by two affine varieties. So let's have a look at what's Km sigma check. So what we do is we take this region inside the two-dimensional rational vector space and we look at the lattice points inside here. So certainly you get the lattice points on this line, so this will include -1, 1, which I guess if you want to write this as, you know, powers of x and powers of y, you've got a positive power of y and a single negative power of x, so that's y on x. And you can look at all the powers of y on x, and that will get you all the lattice points on this line. And then for this orange region, you can take any of those points on the line and you can slide it across to the right as you like. That means you can multiply them by any power of x. And in that way, you can get all the lattice points in that orange shaded region, okay? So this Km sigma check, this monoid algebra is just the polynomial algebra in x and y on x. So this is actually going to give us a copy of the affine plane with coordinates x and y on x. We can do the same thing with M tau check, and I hope you can kind of guess, you just swap the roles of x and y. So that's going to give us affine plane. But now with coordinates, instead of y and x, you get x on y, and instead of this x, you get y. So x on y and y. So you're just gluing two copies of the affine plane together. And how do you glue them together? So what you do now is you look at the intersection of sigma and tau for the gluing. And that's why this picture is nice, okay? Is because when you want to intersect these open sets corresponding to sigma and tau, you look at just the intersection of the cones. So let's look at that, and you look at that sigma intersect tau, and you look at the dual cone. And the dual cone here is anything that has non-negative inner product with it. So it's anything above this line. Now note that this cone is not actually strongly convex. So on the M side, it may be that you have a vector like this one here, which is not zero, and its negative is also inside here. Okay. So that's something that you have. Okay. So this will be a cone which contains the both sigma check and tau check. And that's one of the reasons why this is a nicer one to work with combinatorially. You can visualize it a lot nicer, and the conditions which define it are easy to see, okay? So this one, often you can read off more information, even though, of course, this kind of gives you equivalent information, okay? But this is a lot messier picture. Anyway, let's have a look and see what the intersection is. So how you're identifying a principal open subset of this with a principal open subset of that. Okay, so I guess if you work on the orange side, this sigma check, you can take this orange region and you can slide it back down along this line as far down as you like. So in other words, you can take this, well, this will correspond to x inverse y, so y on x, and you can invert that as you like. So you can take what's here, x and y on x, and you can invert the y on x as well. Okay. Or similarly, you can take this purple region and slide it back up along this diagonal line by inverting this. So you get k, x, y, y, that's what we had for tau check, but now you invert the x on y as well. So you throw in the inverse of x on y. And that's how you glue these together. And that will give you a new toric variety. Well, if you know your algebraic geometry, hopefully you can see that this is a familiar sort of variety, okay? But if not, one thing that you can say, which will help you understand what's going on, is that if you look at these two, so firstly, all these inclusions, they're kind of nice. These morphisms, okay, I don't really have to define them other than to say that they're sub-algebras of some fixed algebra. And in fact, it's the sub-algebra of the Laurent series. Furthermore, the sub-algebra, everything's a sub-algebra of Km, which is the Laurent series, or Laurent polynomials rather, in two variables, x and y. Okay? And so you'll find that there's a map from kxy into both of these, okay? And that's just given by, well, this is a subalgebra of this, okay, because when you multiply x with y and x, you get y. So this contains both x and y. And similarly, when you multiply x on y by y, you also get x. So you'll get kxy as a subalgebra of this as well. So that means that you have a map from this copy of the affine plane to this copy of the affine plane, spec kxy, which is A2 with coordinates x and y. And similarly, you have a map from this copy of the affine plane to this copy of the affine plane. And on the intersection of these two, as an open cover of this x delta, they agree. So that means that you can actually map all of x delta, not just these affine open subsets, all of this x delta to this A to xy. And so that's the map that you get. And then you can ask yourself, well, what's happened here is that in fact, x delta here is the blow up of A2 at 0, 0. Okay, so that's basically what's going on. So what is A2xy as an affine toric variety? That's just given by this positive quadrant, if you like. And it turns out that if you want to blow up, what you do is that you just chop that into two, into this sigma and to this tau. Okay, and that gives you the blow up. Okay, so and hopefully if you know your algebraic geometry, you would have seen this. That's how you construct the blow up. Okay, so you have this copy on affine plane like this, and this copy as well for the other part, and you glue them together, and this is the gluing map that gives you what you want. And there you have it, how you do a blow up using toric geometry. Okay, so the simplest one here, you've got this affine plane given by the positive quadrant, and then just to blow up, what you do is you take essentially you take the generators, there'll be 1, 0 and 0, 1, and you form a new cone that's generated by the sum of those two, 1, 1, and you use that to split up this into two cones. Okay, so that becomes the face of the two new cones, so you split it up like that. And that gives you the procedure of blowing up, in this case, of A2. And the final example is something that hopefully you would have seen when I introduced toric varieties in the special case of the projective plane, and that's this one here. Okay, so if you look at now inside the n equals 2 case, q to the 2, and now you have three two-dimensional cones, and you can see that they're all strongly convex. And how do they intersect? They don't overlap except for in this one-dimensional sort of situation, which are faces of each of them. And also those one-dimensionals all intersect in that zero-dimensional 0 there. Okay, so you do actually get a fan. And if you go through and construct this toric variety using this recipe, you will actually recover P2. I hope you enjoyed this adventure in pure mathematics.